Okay, so we're in chapter 1. Physics is the study of the physical world, and physics is the underlying why the world works. So atoms behave the way they do because of physics. When you did atomic theory, everybody you were talking about, they weren't chemists for the most part. A few of them were. Most of them were physicists. My hero, Werner Heisenberg, was a physicist. Rutherford, physicist. So we describe how the world works in a lot of different disciplines, biology, geology. We explain how it works in chemistry, but really underlying that chemistry is physics. So there are a lot of areas of study in physics. We're pretty much going to stick with mechanics. We do some vibrations and waves. We do some optics, and we do some electromagnetism. We don't do thermodynamics. The goal here is to get you ready for a first year of physics. Typically, your first year of physics in a college setting is broken down into 3 equal or not equal parts. Classical mechanics, that's that first bullet point. Usually there's some electricity, electromagnetism, and usually there's some wave phenomena, which does light and sound. That's kind of the standard. Mechanics is how things work together. That's all it is. It's how bodies fall. It's how motion occurs. It's how velocities change. It's how objects stop. It's the very basic physics around us. It hasn't changed in a couple hundred years. Sir Isaac Newton, very strange dude that he was, and believe me, he was very, very strange. You should read about him sometime. He's a weirdo. Very, very brilliant weirdo. But what we're doing is Newtonian mechanics, classical Newtonian mechanics. We're going to calculate trajectories. We're going to fling ping pong balls into the air at different angles and see how far they go. We're going to track the motion of little battery-operated cars. We're going to drop things. We're going to throw things. That's all classical mechanics. We spend a lot of time on that because you'll spend probably a third to a half of, if you do college physics, a third to a half of your first college physics will be classical mechanics. Anybody who's heading for an engineering discipline, that is all based on classical mechanics. If you're heading for civil, mechanical, architectural, any of those kind of disciplines, that's classical mechanics. It hasn't changed in a couple hundred years. It's not all that exciting. Well, it is, because we get to launch things. But it's pretty basic. We do a lot of that. Thermodynamics is the science of how heat is exchanged. My faraway, distant dream that I don't think will ever happen is I want to have a physics class where we get to do thermodynamics and we build different designs of solar water heaters and we test them and we do stuff like that. But oh well. We don't get to do much with thermodynamics. Mechanical engineering does also delve into thermodynamics because you look at how you shed heat off a system. That's one of the big things that mechanical engineers have to think about. When you have materials moving together, they heat up. Friction. So think about who here arrived this morning in something powered by internal combustion. Okay. Nobody rode a goat cart. Nobody rode a pony. Nobody walked. We don't have a whole lot of walkers. That's okay. Every couple of years we get like 2 walkers. So internal combustion. I just want you to think about this for a second because I have a 3.5-year-old, 3.8-year-old now, 3.8 I think. I get a lot of questions, and we tend to give really detailed answers, which, oh well. Mama, what makes the car go? Well, it's an internal combustion engine. Do you know what that really means? The internal, what does that mean? Inside. Combustion, what does that mean? It's on fire! Is this safe? No, it's not safe. Of course it's not safe. You're driving around with a bunch of controlled explosions happening 2 feet in front of you. Does that sound safe to you? Yeah, it's like it's fine. What could go wrong? No, it's not safe. You've got controlled explosions happening 2, 2.5, 3 feet in front of you. If you're driving one of those, 1980s big vans with the doghouse, the engine is sitting a foot from your leg. They really get hot. How do we deal with the heat in that system? There's something on fire. Thermodynamics is thinking about how you shed heat out of that system. How do you shed heat out of that system? How do you dissipate that heat to the environment? If you let that metal just keep heating up, it'll melt. Radiator. Who said radiator? Yeah. Yeah, the radiator. So the radiator just sucks heat off the engine? How's it work?
From the news water.
Okay. Has something to do with some sort of, I'm going to replace water with fluid. Because if you use water, actually, that doesn't work so well. Some kind of fluid. What does the fluid do? Yeah, it cools it down. How does it cool it down? It exchanges heat with the engine. You send a cool fluid into a hot engine. The fluid absorbs heat from the engine. Yeah, it's coolant. Yeah, antifreeze. It's used to cool the engine. It also prevents it. You have to use antifreeze, not water, because of course in the winter it would freeze solid and crack your block. But then you've got hot fluid. What do you do with that? I saw somebody doing pantomime of what you do with that in the back. Go ahead, Drew.
It goes through the radiator where it just puts the water through narrow little pipes and air runs past and it cools it down.
Yep.
Goes back in the
Exactly. So you cool it down by putting it out front and running cool, nice cool air over it. People tend to run into problems driving through places like Death Valley, where the air temp outside is 120 degrees. Even if you're moving fast, you're not cooling the fluid sufficiently. So even a properly operating vehicle with good coolant can overheat in a situation like that. There are limits to what you can do thermodynamically. Thermodynamics is as simple as the fact that hot air rises and cold air drops. It has to do with density. Sadly, we don't do a whole lot of thermodynamics. Vibrations and wave phenomena, we do a section on this. This is everything from the sound that you're hearing right now, the things that you're seeing because light is bouncing off objects, hitting the receptors in your eye and forming pictures in your brain. It's amazing. It's miraculous. It's fantastic. It's astounding. I can see all of you people. It's cool. And the optics gets a little bit more into that phenomena of vision, phenomena of light, how light behaves. We talk a little bit about lasers. We do a lot with mirrors and reflected images, curved mirrors, flat mirrors. We typically don't get to do a lot with lenses, but we sort of brush on those. Electromagnetism. Really, optics and electromagnetism can be thought of as subsets of the wave thing, because electromagnetism, the stuff that's running the lights up overhead, the stuff that's running the Apple TV, the stuff that's running the iPads, it's a wave. Actually, it's two different waves joined together at right angles, and there's all this space in between them, and it gets kind of weird, but it's waves. It's wave behavior. We do some circuitry in here. You will build circuits at the end of the year, or maybe the midpoint of the year. I don't know. We'll think about it. It's cool. You get to solder. Electromagnetism includes the great mysteries, such as, I have a paper clip. It's very attractive to the earth. It falls. Every single time. I keep testing this, it keeps falling. The entire mass of the earth is pulling on this. Okay, so we know that. We get it. Ha ha! I win. I just beat the earth. I just beat the earth. The entire mass of the earth is pulling on this paperclip, and I'm holding it up with a 10-cent magnet from Radio Shack. 10-cent magnet from Radio Shack? versus the Earth. 10-cent magnet wins. Does that strike anybody as weird? It is. It's amazing. Electromagnetism. Magnets, electricity, we can generate an electrical field with electricity, electromagnets. Okay, we'll do a little bit of electromagnetism. Relativity and quantum mechanics. Has anybody taken the course at Kent, 7 Great Ideas That Shook the Universe? Something like that?
My sister took it.
Took it? Okay, it's supposed to be really cool. I call it cocktail party physics. Because it's the kind of like cool, amazing, mind-blowing physics that allows you to wear a black turtleneck and sip beverages out of sophisticated-looking glasses while looking very glamorous and sounding very smart. It's good stuff. And it's cool, and it's mind-blowing, and it's weird and wild, and we don't do it in here. Sorry. This is always when I get people... They're like, are we going to talk about string theory? Are we going to talk about the origin of... No. I'm sorry. We're going to fire ping pong balls at things. We're going to drop bags of flour. We're going to throw eggs. We're going to build stuff. We're not going to talk about relativity. Relativity was Einstein's contribution to physics. Relativity has to do with time and space itself. It has to do with why gravity works. Why does gravity work? We don't know. You know that? We don't really understand why gravity works. My hypothesis, rubber bands. But anyway, we don't get into relativity. It's just too far out. There's a nice chapter in the back of your book. You're welcome to cruise through it on your own, but we're not going there. And quantum mechanics, do not mix up classical and quantum mechanics. They look like they're related, not so much. Quantum mechanics is the stuff of tiny little particles. So subatomic particles. Protons, neutrons, electrons, getting weirder quarks and preons and all kinds of weird stuff. I can't even keep it straight. We don't go there. The reason relativity exists, the reason that Einstein basically came up with this stuff, is that there's a fundamental belief in science that the same rules apply everywhere all the time. Because how can we understand phenomena if the rules change? If things work one way this time and in this place, and then they work another way in a different time and place. So we assume, for instance, right now there's have you guys heard about exoplanets? Have you been hearing? Maybe you don't listen to the same news I do. Okay, good. There has been this boom in discovery of exoplanets. Those are planets orbiting suns other than our own. And there are a lot out there. They just found one that they think is in the Goldilocks zone. Not too hot, not too cold. It's the Goldilocks zone, just right. They have found exoplanets by watching the behavior of distant stars that wobble. Because the gravity of a planet is pulling on the star. Well, we can't do that unless the laws of gravitational attraction work the same way every place else in the universe as they do here. Because if they don't work the same way every place else in the universe as here, then we have no idea what's happening out there. I don't know. Why is that star wobbling? I don't know. Had a bad night? Feeling a little bit dizzy? I don't know. It's cold. It's hot. It's got a headache. I don't know. So we have to assume that. Great. Good. We assume that everything at a big scale. Why does a 3,000-pound car behave the same way as a 1.5-gram paperclip? Drop a car, it falls. Drop a paperclip, it falls. They behave the same way. Good. No matter how big you are, you can't avoid the laws of physics. You can't do it. The laws operate the same way all the time, no matter how big, no matter how small, no matter where, no matter when. Except that they don't. They don't. Once you get down below the subatomic level, things change. They do not operate the same way, based on the rules that we can understand. And as that was starting to become understood, it was Einstein who really kind of freaked out about that. And relativity attempts to start to reconcile the fact that things on the macro scale, things that we can see, and things on the subatomic scale work a little bit differently. That's what relativity does. It's not finished. We still don't understand if there's some bigger overarching set of rules that's driving the two sets of rules that we can observe, so that in fact the rules are the same. We're not sure. But a lot of people are spending a lot of time thinking about it. Note that there's not a whole lot here. Note that scientific methods is plural. And I suspect that you've done the scientific method every year since 6th grade. Is that correct? Okay. We're not going to spend a whole lot of time on it. What I want to talk about is just scientific ways of thinking. Science has to be, it's got to be observational, it's got to be objective, it's got to be factual. We try to explain phenomena that we have observed, that we have measured through making hypotheses. That's, once we get past raw data, we're no longer, data is objective. The minute you start to explain it, you're there with everything you bring to the table. All your assumptions, all your prior knowledge, all of your own biases. I mean, I have this crazy bias. I really think that every time I let go of something, it falls. Based on a lifetime of experience. Kids start testing this out at about 7 months of age. It's seriously, I mean, it's a phase they go through. They push things off tables. Ooh, look. Oh, look, it still works. Oh, look at that, it works again. They're testing. They're tiny scientists. It's amazing. A hypothesis is a working explanation for observed phenomena. I hate the whole educated guess. Hypothesis is an educated guess. It's not any kind of guess. It's your working explanation. It's the best explanation you can come up with based on the observations you've got, based on the data you have. And it can be tested. And so once we test it, once we have some kind of result, we have to interpret it. We have to evaluate our results. And we draw conclusions from that. We discuss. Science is all about discussion. This year, thus far, I haven't had time. I try to read one Science Daily article per day. It's a fantastic website. I'll link it to the physics page. You can search topics. I used to try to have physics students summarize an article. I didn't feel like it was useful, so I quit doing it. But you publish, you share, you put out your conclusions so that other people can compare what they're seeing to what you've seen. Okay, I do want to talk a little bit about models. So experimental design, if you're going to test something, you have to be able to describe it in some way. When you're building a hypothesis, honestly, a hypothesis is a model. Because a hypothesis is an explanation. It's a representation of how you think it works. And models are not just little tiny replications of the real thing. My lucky frog. I should have a dare going to see if you can find how many of them there are in the room before the end of the year. Anyway, it's more than just a little teeny tiny version of the real thing. Models can be mathematical. In all of the science about climate, okay, there are 3. You got them all, okay. They're not very well hidden right now. I plan to add more through the year just to mess with people's heads. There was a great book I read years ago. I got, I guess it was bronchitis. I don't know what it was. I was basically on my back for 3 days. This was pre-child, pre-husband. Hey, I got 3 days to do nothing but read. Cool. And I had this book that had been sitting on my shelf for years, and it was really dense, and it was really thick, and nobody was going to be talking to me for 3 days, so I holed up and read it. And it was written by this awesome, brilliant climate scientist, and he talked about having an undergrad. He taught at, I don't know where. University of Wisconsin, I don't know, having this really excited undergraduate come up to him and say, because he had been discussing climate models and the climate model that he was working on. And he had worked with this climate model for many years, and they kept refining it. And this undergraduate who was going to say, can I come see the climate model? Nope. Because the climate model was all math. It was mathematical. It was in a computer somewhere. You can have a mathematical model. You will do some mathematical modeling in this class. When you describe the motion of an object that's being thrown up at an angle, you're creating a mathematical model for that motion because you have an equation that describes something in the real world. That's a mathematical model. You've been doing them in algebra, you just didn't know it. Maybe, do you talk about the fact that they're math models in math? Okay, good. Physical models are the ones we all think of. That's my little tiny frogs. Beaver Valley Nuclear Power Station, anybody got family, friends, loved ones, neighbors who work there? Anybody know where it is? Go right down Calcutta Smiths Ferry Hill. Hang a Midland. I can't tell left from right. But my dad worked there for years, and they had the model. He used to do, he was on the speakers team and did tours and stuff, so I got to go on lots of tours as a kid, because if there was a day off school and Dad was doing a tour, I got to go. The model was, at the time, this is in like 1986 dollars, $1.3 million worth of plastic. And it was an entire scale replica, whoops, of the entire plant. Every tube, every valve, every ladder, every entrance, everything in plastic. It took up a room about 3 times the size of this. It sat in the office building that he worked in. And it was on all these tables, sort of joined together. It was all covered in plexiglass. And he would take groups through the model. They had built that model because, though it cost $1.3 million, if you had gotten into construction and realized that on those 2-dimensional blueprints you had 2 pipes that were actually supposed to be in the same place, that would cost more than $1.3 million. So it was cheaper to build a full-scale 3-dimensional. Now, today, they wouldn't do that. What would they do? 3-dimensional computer rendering. Yeah, it wouldn't be necessary today. The technology has improved. You would no longer build that model. And the model disappeared at some point in the 90s. And I had a student 2 years ago? Yeah, 2 years ago now, because it was in the old school. And I said, I was telling this story, and I said, and I don't know what happened to the model. My dad always thought maybe it got thrown in a dumpster. What a shame. Her dad worked at Beaver Valley, and she went home and she said, "Hey, Dad, have you ever heard of the model?" And he's like, "Oh yeah, the model." It's still in the storage room. It's still there. They didn't throw it away, which is nice. That's a physical model. That's the one we all think of. A verbal model is a description. Hypotheses are verbal models. They are explanations of how things work arranged in words. You also do verbal modeling in math. When you go from a word problem to just the numbers and symbols, that in-between step is the verbal model. You're describing verbally what's happening mathematically. And visual models, well, those are pictures. I have an awesome, brand new, well, it's not brand new, it's very old, but I just found it, visual model of all the rivers on Earth. I'm getting it laminated because I think it's awesome. That's all the rivers on the Earth. Wow. It's a visual model of fluvial systems on terra firma. Kind of cool. A visual model can also take the shape of something like this. This is a visual model. On the back side of it, how much water is used for things you didn't think used water. You have visual representations of relative quantities of something in a process. That's a visual model. Okay, in physics, we don't do the same kind of labs you did in chemistry. However, there are physical experiments in physics. So those physical models can be used to run simulations of things. There are physical experiments going on, like the Large Hadron Collider, where they are throwing particles together at high speed under the Alps to smash them together to see if they create black holes and destroy us all. No. But a lot of physics takes place in the form of thought experiments. Einstein was famous for thought experiments. There's no physical setup in a thought experiment. There's Einstein sitting in a chair. And there's a verbal model that he's building. And he's testing that verbal model. Well, if someone is on a train, and if that person on a train is traveling past a city with a clock tower, they can observe the clock tower, but they are traveling, and time, what would happen if that train approached the speed of light? What happens to their observation? That's a thought experiment. I don't know what happens. A controlled experiment is the kind of thing that we usually talk about in biology. It's done in physics as well. You have a control group, you have an experimental group. One group gets something the other doesn't. I think you know those. Okay. Measurement. We measure a lot in physics. Your measurement skills are really important. This was one of my other things on my little page of things to say about physics labs. Things not to say in a conclusion. We had lots of human error. No kidding. I can't measure to save my life. We'll talk about parallax in a little bit. I'm a lousy precision measurer. Terrible. I know this. My cuts are always weird. I do some woodworking, and my cuts, I struggle really hard. So measurement, it's a skill. You can build it. But we're going to talk about it. There are two big things in measurement that we're talking about that I want you to be very clear on. Dimension is the quantity that you're measuring, length, mass, time, brightness, amount of a substance, moles. Units are not the same as what you're measuring. You're not measuring meters. You're measuring length. You're not measuring grams. You're measuring mass. You're not measuring seconds. You're measuring time. So that's just a quickie. Now, and this is where we're going to stop today, page 12. If you would be so kind, you know what? No, we have 10 minutes. Okay, we have 10 minutes. Grab yourself a physics book. Read it, love it, live it. And yes, know how to convert it. I will put the tutorials up. So here's the way I do this. I don't tell you have to. I'm not going to ever give you a chart that you have. Oh, actually, that wouldn't be a bad idea. Let me reconsider that statement. In the past, I've not, I don't give you a chart. I don't test you on if you can fill in all the powers of 10 and all the prefixes and all the abbreviations. But what I say is that basically, starting from your first test, I'm going to assume that you know these things, and I'm going to freely use the abbreviations and assume that you know that micro is 10 to the negative 6th, that kilo is 10 to the 3rd, that centi is 10 to the negative 2nd. Here are the ones that you are responsible for. You can see that they have been circled many times in my book. Pico, nano, micro, milli, and centi on the low end. And these are easy because they're all multiples of 3. 10 to the negative 3rd, 10 to the negative 6th, 10 to the negative 9, 10 to the negative 12th. Centi is the weird one, 10 to the negative 2nd. And then on the high side, I expect you to know deca, kilo, mega, giga, tera. We very seldom use giga or tera. We very seldom use pico. But they do come up. And I ask that you do conversions using powers of 10, especially in here. I train chem kids to do them that way, and I think probably Mrs. Haylett does too. It's more important in physics than it is in chemistry. Chemistry is kind of the conditioning for it, but doing it that way, because now you're going to be dealing typically with much larger and much smaller numbers. You'll be dealing with actually a fair number of megas and micros, 10 to the negative 6, 10 to the 6th. So I will put up the tutorials on here. I'm going to do a brief very brief, 4 minutes, run through on doing a conversion. I'm going to go ahead and, I mean, heck, it's points for you. On page 14, we'll do your first assignment. This is section 1A, numbers 1 through 5. So that'll be homework. They're pretty easy, and actually, we'll just go through, number 1. No, that's too easy. That's too easy. We'll do the sample problem together. So bacterium has a femto. Who uses femto? Apparently bacteriologists. Has a mass of 2 femtograms. Express this measurement, we'll go to kilograms. So if we have 2.0 femtograms, and we would like to know how many kilograms that is. We know, and this is dimensional analysis, you just never knew you were doing it, that units have to cancel top to bottom. So the box directly next and below is going to be femtograms. The way that I teach this, we always, every single time, go through base. I find it much easier, and it avoids common trip over your feet kind of mistakes. So when I say go through base, the way that I'm a really visual learner. The way that I visually have this arranged in my head is 10 to the negative 12th, 10 to the, oops, sorry, backwards. I'll do this with an abbreviated version. Base, or 10 to the 0, and then, 10 to the negative 2nd, 10 to the negative 3rd. So I visualize it as sort of a tower where we've got our positive powers of 10 above base, above the line, and our negative powers of 10 below. When I say always go through base, those power descriptions, 10 to the 3rd, 10 to the 9th, 10 to the negative 2nd, are all the relationship to the base unit. They're all the relationship back to grams, meters, moles, newtons. So we know that we're looking for a relationship between grams and femtograms. Femto, I hate that. In our last box, we know that units have to cancel. Grams, kilograms. Quick check, do our units cancel? Femtograms, femtograms, grams, grams, we end up in kilograms, that's what we want. Then we can start to plug in powers of 10. So in this case, what we're looking at on this chart is this number. So 1 femtogram is 10 to the negative 15th grams. When I teach this, the way I teach this is the power of 10 always goes with the base unit. Always. It doesn't always go on top, it doesn't always go on bottom, it always goes with the base unit. If you remember that rule, you will never screw these up. I promise you, I assure you. So 10 to the negative 15th, and this is 1. Because 1 femtogram is 1 times 10 to the negative 15th grams. Now, kilograms, what's the power of 10 associated with kilo? 10 to the 3rd. So 1 kilogram is 10 to the 3rd grams. These are the ways that I avoid making mistakes, because I know where I trip over my own feet. I've made every mistake you can make in physics. I've made most of them 3 or 4 times. So what I try to do very hard is tell you where I know the pitfalls are, so that you don't make the same mistake I do. Go out and make your own mistake. Go out and make a new mistake. Seriously. So I convert everything to scientific notation because I can't move decimals to save my life. I screw it up every time. I screw it up. I do. So this one's easy because 2 is just 10 to the 0. Okay, We'll pick it up tomorrow. I would suggest that you do these homework problems tonight. I will post all the tutorials tonight. They're not due tomorrow. The chapter 1 homework won't be due probably for at least a week. But I would suggest that you do those tonight because that's how the system works. Hey, have a good day, folks.